Hi everyone, thank you for joining. So in this video we're going to talk about the experimental evidence supporting Einstein's special theory of relativity. I think the first one we're going to talk about is a well-known experiment which was carried out in 1971, and the idea was to have two clocks here. These are atomic clocks. Yeah. Two identically synchronized atomic clocks, and the idea was to put the second clock on a jet plane, right? So we put it in a jet plane here, and then what happens? Let me call this 1. This is 2. So this is clock 2. And with the jet plane, the clock would be traveling all around the world, and then we would bring it back to and put it next to the first atomic clock, and then see the difference, if there is a difference. So how does the motion affect the time, right? Now, what is quite crucial here, that if you remember my previous videos on special theory of relativity, one of the things I said was the time dilation is not like something you have two tables and two people working on doing the same job, same amount of job, right? But the first person is much faster. Because he is faster, it takes him less time to finish the work. And then I pointed out, when we talk about the time dilation in special theory of relativity, it has nothing to do with this. It's time dilation is about the nature of time. You know, what do we know about time? And it turns out that it has this very peculiar feature, and I like this experiment very much, although there are some difficulties involved in this experiment. I like it very much because it shows that point very clearly, that the slowing down or the time dilation is a property of time. Then that's it. That's the full statement. It belongs to time. It's property of it. Yeah. Okay. Now, first of all, if I remember it correctly, they use atomic clocks. And what are atomic clocks? Atomic clocks are much more accurate than any other clock we have. So I think what they used was the cesium 133. Okay. So no, they use an isotope of it, if I remember it correctly, right? So the 1 second in these clocks are defined to be, well, the 1 second is defined to be 9,192,635 and 770 vibration of the light with a specific wavelength emitted by cesium 133 atom. Right, so these clocks are very precise clocks, and it had to be. So the second clock was put on a jet plane and went around the world. Yeah? And then what happened is that they brought the second clock after the journey right next to the first clock. And what was quite remarkable is the second clock was, I think, approximately 200 nanoseconds was behind. Yeah, now that's quite crucial, and that makes the point very clear. The time changes, it slows down, something happens, you know, when you're traveling, and it's the property of the time. Of course, there are, by the way, this 200 nanoseconds would have been precisely predicted by relativity. This is what's even more shocking, that the theory predicts this 200 nanoseconds. Of course, there were difficulties. For example, jet plane is not that fast when you compare the speed of light. It's extremely slow, and moreover, it's not going to be inertial reference frame, because plane will be accelerating, decelerating, changing direction. But despite all the difficulties, that this provides evidence that Einstein's special theory of relativity, the predictions are correct, and which is quite remarkable. Yeah. This was the first experiment I could think of, and the second experiment is particle physics. So second experiment is about muons. What are muons? Well, the muons are created at the top of the atmosphere at the height about 60 kilometers. Well, when you have a high energy cosmic rays collide with the air molecules, this is how muons are created. Yeah, and it is well known that the half-life of muons is about 1.5 microseconds. Yeah. Okay, so what does it mean, half-life? Well, if you have some bunch of muons here, so it takes 1.5 mus to half of it to decay, and the other half is another 0.5 mus, and then the other half, and so on. Yeah, okay. Now we can use this decay as a clock, right? So what happens after muons are created? Let me draw this. So this is Earth, right? And they are created somewhere there, which is about 60 kilometers. And once they are created, they start traveling in every direction, and including towards Earth, right? So what happens is that when they travel, it is known that the speed that they travel is nearly the speed of light. Yeah. So in other words, how long does it take for muon to reach the Earth? Well, we have delta T is equal to distance, which is 60 kilometers, divided by the speed, which is about 3 times, well, let's say it's traveling at the speed of light, okay? And what will that give us? Well, that will give us about around 200 microseconds, yeah? Okay, so that's delta T. All right, now we know the half-life, as we said, the half-life is 1.5 microseconds. So if we do 200 mus divided by 1.5 mus, we're going to get approximately 133. Yeah. So what does it mean? So it will take 133 half-lives for muons to reach the Earth. Yeah. So only some fraction of the muons will be reaching the ground. So, and how would we work that out? Well, that's half-life to the power of 133, which would be about some 10 to the minus 40. Yeah. Now, what does this mean? Well, what does this tell us? It tells us this. It tells us only 1 out of every 10 to the 40 muons reach ground. Okay, so only 1 out of 10 to the 40 muons will reach, okay? But then you make a measurement, and what you see is you see this: 1 out of 10 muons reach the ground. Now, this is very much different, as you know, as you can see the difference between 10 and 10 to the 40. Yeah, so it differs by a factor of 10 to the 39, which is all right. Now, how does that happen? Well, this is explained again by Einstein's special theory of relativity. So, if we do a simple mathematics, remember when we talked about the 200 mus, we're talking about this has been observed by Earth reference frame. But if we observe it from the muon's reference frame, notice that the muon, let's say muon is created here and it reaches Earth there. So these are spatially different, but if you are in the muon's reference frame, that means you're looking at the same clock. In other words, we're looking at the proper time. So we have delta T is equal to proper time divided by 1 minus v squared over c squared. Now, we did say that muons travel almost at the speed of light, but it's not quite exactly the speed of light. So it's slightly less. So if we take, for example, I think there are experiments, measuring the speed of muon, but let's take v to be 2.999 times 10 to the 8, which is very close to the speed of light. Yeah. So if we do that and plug it in, we have delta t, which is 200 mus, is equal to delta t divided by 1 minus 2.999 99 divided by 3 squared square rooted. So we're using the formula 1 minus v squared over c squared, right? And if I get my calculator, so if you plug this into a calculator, you will see that delta t turn out to be about 5 mus, okay? So in other words, as you look at it, so the previously what is observed from Earth was 200 mus, now it becomes that. Instead of having half 133, what are we going to have now? Well, we're going to have half 3.3, isn't it? And where did we get that 3.3 from? Well, it's 5 divided by the half-life. Yeah. Okay, and you can see now that that will give us 3.3. So what does that mean? Well, it simply means it's very consistent with the experiment now, because if you look at 1 over 2 to 3.3, you get something like 0.1. In other words, 1 out of 10 as measured by the experiments, right? Okay, right. So I think it's wonderful that when we have the sophisticated enough instruments to measure and test the theory, and find the evidence supporting the theory. So these two examples were two evidence supporting Einstein's special theory of relativity. There are plenty more evidence, especially in particle physics. Now it's quite advanced and sophisticated. So, but I think two experiments is good enough to have a intuitive understanding on how to use special theory of relativity and how these provide evidence to special theory of relativity. Okay, excellent. Well, thank you so much for joining. I hope to see you in my future videos. Thank you.